Hello, this is question 5 from the 2007 MAT. We have some function of n defined as follows. For any integer n greater than or equal to 0, we got 3 branches to the function depending on the value of n. So if n is 0, if n is greater than 0 but even, and greater than 0 but odd. Oh, and the bottom 2 branches are recursive, as in we'll be putting the result back into the function again. Right, that'll be fun. So what do they want us to do? They want us to, first of all, work out the value of f5. So f5, that's going to be the bottom branch then. So greater than 0 and odd means we've got 2 lots of f4. So far, so good. That's going to go into the middle branch. And we will then have f4 is f2 squared. So that is going to be equal to 2 lots of f2 squared. f2 will also go in the middle branch. So we've now got 2 lots of f1 squared squared. So f1 squared squared. And f1 is back to the bottom branch, is 2 lots of f0. So 2 lots of f0, that needs to be squared, and then we need to square it again. Okay, this is a recursive mess, but I think we got to the bottom of it, because f0 is then 1. So this means we've got 2 times 1 squared, so 2 squared squared. What did I just say? 2 lots of 1, so 2 squared squared. That's what we've got. So that's 2 to the 5, otherwise known as 32. Right, okay, that was fiddly rather than anything else. The recursion depth of fn is defined as the number of other integers m, such as the value of fm is calculated whilst computing the value of fn. What? For example, okay, the example might help. Recursion depth of f4 is 3 because the values f2, 1 and 0 need to be calculated. Right, okay. Right, that makes more sense. Not too sure what I was saying in the other bit. But we've got, yeah, so f4 has got recursion depth of 3 because we used a 2, a 1 and a 0 in there. So they want the recursion depth of f5 is what they're asking here. So it's going to be 1 more than the recursion depth of f4 because we just used 4 in there as well. So that is going to end up being 4. Right, that was okay. Second part of the question here. We got a new function, g, defined for all integers, again, n greater than or equal to 0, as follows. Right, there's some similarity between these functions, as in the bottom 2 branches, they're doing the same operation on n. We're halving it in the middle one and we're taking 1 off in the bottom one, but it's got a different calculation. Okay, so what is g5? Right, so g5, yeah, so that'd be bottom branch again, it'd be 1 plus g4, and g4 is 1 plus g2, so that's going to be 2 plus g2. g2 is 1 plus g1, so that's 3 plus g1. We've got a good bit of counting going on here, a 1, a 2, a 3. g1 is 1 plus g0, which is just 1, so that equals 4. So yeah, we counted up 1, 2, 3, 4. It's counting steps. I think this is probably counting the recursion depth, I imagine, what's going on here. So that's worked out that. What is g2 to the k, where k is greater than or equal to 0? Right, okay, so that's certainly greater than 0 and even. Well, I suppose unless k is 0, in which case it's the one at the bottom. So what's going to be happening with this? Let's try out some values. I think might be wondering whether to do it as a general case straight off, or let's try out values, get a flavour of what's going on. So k is equal to 0. That will mean that we've got g of 1, which is going to be equal to g of 1, that's the bottom one, isn't it? Is going to be 1 is just 1. Right, k is 1. We've got g of 2, which is 1 plus g of 1. Okay, k equals 2, g of 4, I should say, which is 1 plus g2, which is 3. Okay, so we're just counting up. So this is certainly pushing us towards the answer being k plus 1 for this. That would be our g2 to the k. So briefly explain your answer. I don't think that's quite enough for giving a valid answer on this. So what is actually happening then? So every time we can see, every time we're doing a loop, whatever one we do, we're adding 1 on to the total. So that's one thing that we can say. And it's also, we're always going through the middle branch until we reach the bottom. And the middle branch is taking 1 off the power because we're dividing by 2. And it keeps doing that until we hit the bottom and we just get a final add 1 on. Right, so let's write something fairly coherent out about this. So let's say each loop through G adds 1 to the total, and it reduces the power of 2 by 1. Power of 2 by 1. So therefore, let's go over here. Therefore, we can perform a total of k plus 1 loops, because that is taking the power from k, where we start off with, down to 0. So we've got k all the way down to 0. So that is going to be k plus 1 loops. Therefore, total is equal to k plus 1. Right, okay, so I think that's better than just setting this out and saying, oh, well, it looks like it's going 1, 2, 3, 4, 5, 6, you know, actually give a bit of an answer to it. Right, I've got a duplicate of this sheet, which I'm going to need because I run out of space. Now, where do we go up to? We got up to part 5. Right, so what is g of 2 to the power L plus 2 to the power k, where L is greater than k? So, right, and they're both integers greater than or equal to 0. Okie dokie. Briefly explain your answer. Right, well, we know the basic process that happens when we're using function g. We're reducing the powers down by 1 each time. So every time we loop through g, we add 1 to the total and reduce the powers down. So let's start from that point of view if we know what happens. So we know from part 4, that each loop through g of g adds 1 to the total, and reduces power of 2 by 1, reduces each power of 2 by 1. Right, so that's fine. So what's going to happen then? We're going to keep on doing this. When does it break out of that middle branch loop? Once we've done this, well, it's going to keep doing it like it did before until it hits an odd number, and then something changes. So when are we going to get an odd number? We're going to get an odd number after k loops, because we're going to have a plus 1 on the end. So we can say, therefore, after k loops, we can then say, right, so g 2 to the L plus 2 to the k is going to be equal to, that's our counter, that's our k counter. We've done k loops, and then we're doing g of 2 to the L minus k plus 2 to the k minus k. And I've written it that way just so it makes it clear what we've actually done. We've done our counter of k, and we've reduced each power by k. But this is going to be a plus 1. So that is k plus g 2 to the L minus k plus 1. That means we're going through the bottom branch. So that equals k plus 1 plus g to the 2 to the L minus k, because that's what the bottom branch of the function does. Okay, that's great. Now we know what happens with this one, because that was our result from the first. We get from the previous part of the question, we're going to get the power plus 1. So that is equal to k plus 1 plus L minus k plus 1, which is L plus 2. L plus 2. Okay, right, that's good. So I think the explanation here hinges on this, just explaining that you know what the function is doing. Every time we go through, we're adding 1 to the counter and dropping the power down. Okay. Explain briefly why the value of g of n is equal to the recursion depth of f of n. Right, yeah, well, this comes back to what we could see earlier on. It's doing the same thing. Like if you're in the middle branch, you're dividing by 2. If you're in the bottom one, you're taking 1 off. And it's doing exactly the same thing here and here in G. So it's doing the same steps for N. So, right, we need to explain y is equal to the recursion depth of N. Right, so we need to say, what are we going to say? So G of N has the same number of steps i.e. recursion depth, same number of steps as f of n, because it performs the same operations on n, because it performs the same operations on the same, over here, am I going to run out of space? Same operations on n. Right, so that's the first thing. Then we can say that g function of n adds 1 to a running total at each step. So the value at n is equal to 0 is the total number of steps. So final value equals total number of steps. Okay. I mean, it's hard to know exactly what they're going to consider to be a full. I mean, it does say explain briefly. I think it's spotting that they're performing the same operations on n, I would say, was the key to that. Yeah, you can always debate exactly what you think the key point is going to be on these, but I think that's sufficient for a brief explanation. Yeah, it was quite a tough question, that one, I would have said. It's definitely, in my mind, the most difficult one that's been on this 2007 paper so far, but maybe it's just my preference for geometry questions rather than these recursion questions. I don't know. But there you go. I think that was quite a tough one.